Okay, here's a released free response question from 2006 that deals with acids and bases. Let's solve each part at a time. They begin by giving you the balanced chemical equation for benzoic acid dissociating. So there's your benzoic acid, and in an equilibrium process, it exists as the benzoate anion as well as hydrogen ion, but not very much since the K sub A is very low for this weak acid. Important note, for this question, they point out that they have a 25 ml sample that's an aqueous solution. Therefore, we're going to treat this as fully dissolved. I would cross out that S at this point and write AQ. That's important because when we do the equilibrium constant expression, we're going to include that as a denominator. We're not going to omit solids and liquids since it is an aqueous solution. It also means that when we figure out how much of it is in solution in a later question, we're going to ignore the fact that it's sparingly soluble in water, because they could point out that it is an aqueous solution. Okay, so after the addition of 15 mils of 0.15 molar sodium hydroxide in this titration, they're not done. The pH is still acidic. We're going to find out how much hydrogen ion is in the solution at this point. This is really given in a way since the pH is 4.37. That is the powers of hydrogen ion, which means it is 10 to the minus 4.37 molar. So we're going to punch that in, and we're going to remember that the significant figures in pH are always one less than it appears to be. This has two significant figures since it's a log-based system. 10 to the minus 4.37 is the same as 4.3 times 10 to the fifth, and your units are moles per liter. The hydroxide will be the rest of that in the solution. It'll be much lower since the hydrogen ion times the hydroxide ion is always equal to 10 to the minus 14th. Rearranging to solve for hydroxide, we have 10 to the minus 14th divided by 10 to the minus 5th, and that's about 10 to the minus 10th moles per liter. Don't forget your units. Be aware that we have two significant figures. The number of moles of sodium hydroxide added is a straightforward stoic problem because it's given here. They added 15 milliliters of 0.150 moles per liter. So using like units, we should say that we have 0.015 liters times 0.150 moles per liter. Your liters cancel, leaves you with the moles of sodium hydroxide that were added. And in this case, we don't have any pH units, so we have the full three significant figures. We have 2.25 times 10 to the minus third moles of sodium hydroxide that were added to the solution. How much benzoate do we have in the solution? The same amount, since every molecule of sodium hydroxide reacted with benzoic acid to form benzoate. So it's also 2.25 times 10 to the minus 3 moles per liter. You can get in trouble with this problem if you think about it too deeply and you start wondering about benzoic acid, benzoate, and equilibrium constants. But this is a titration. It all reacted. You got benzoate. That's it. Number of moles of acetic acid in the solution. Well, we are assuming that it's all dissolved. After all, they did say it's an aqueous solution. Some of it, however, already reacted with base. It's an incomplete titration, so we can't just say that the moles of sodium hydroxide added is the moles of benzoic acid because it didn't all react. So we have to use the Ka expression, which we very nicely have everything there. And this is a nice example of them leading you down the garden path. Here's your Ka expression. Remember, this is a solution, so it shows up as in the denominator. Do we have hydrogen ion? Oh, yeah, they had you do that right in the beginning. Do we have benzoate ion concentration? Yes, we do. It is given right there in part 4. We have everything except benzoic acid. So I would cross multiply this divided by 1 in order to rearrange for the benzoic acid concentration. And there it is there. You have all three of those numbers. So the concentration of benzoic acid must be 3.7 times 10 to the minus 2 moles per liter. Careful, that's not what they asked for, not the concentration, literally the number of moles. So that's in the solution. So we have to divide that divided by the liters of the solution. How many liters of solution do we have? 15 mils were added to the 25 mils. It sounds like 40 mils or 0.040 liters. That's right there. So liters times moles per liter equals moles, and that's how many moles of benzoic acid were in the solution. Students sometimes get in a little trouble at this point because they start thinking a little further than they should. They talk about the benzoic acid then dissociating, or they start wondering about whether it's like the whole solution or what's left. Are we done? Things like that. Think of this as simply a snapshot in time, right? This is exactly what's going on once you've added your 15 mils. This is the measured, based on a measured pH. This is the actual benzoate concentration. So all this data is certainly accurate. So this must be simply the concentration of benzoic acid in the solution at that time. You could also solve this using the Henderson-Hasselbalch, which is another form really of the equilibrium constant expression. My class has not had buffers yet, so I'm just going to skip it. And then states whether the solution at the equivalence point, so if you did go all the way to the equivalence point, would it be acidic, basic, or neutral? Virtually all AP students know that if you have a strong base, and you do, and a weak acid, it'll end up being basic at that time. However, if you simply say that, they're not going to give you the point. You have to say the reason, and the reason is because the benzoate gets formed in the neutralization process. That is the conjugate base of the weak acid, and it will react with water to make benzoic acid and hydroxide. To me, that's like saying it's a Bronsted-Lowry base, yes, because it generates hydroxide in solution. So here's the exact wording that they like. At the equivalence point, the solution is basic due to the presence of benzoate. That's the conjugate base of a weak acid. And that will hydrolyze to produce a basic solution as represented below. Beautiful. You should try to say it just like they want it. And so you get 1 point for the prediction, and you must have the explanation. But it's all or nothing, 1 point or not. You need them both. In a different experiment, they took some solid benzoic acid that had a little bit of salt in it, which would do nothing at all. It's just some kind of inert, neutral salt that's dissolved in water, and it's titrated with the sodium hydroxide. At the equivalence point, it turned out that it needed 24.78 milliliters of the base solution was added, and there's its concentration. They want to know how much benzoic acid is in the solid sample. Well, now we're at the neutralization point, so the number of moles of hydroxide is the same as the number of moles of benzoic acid. So we figure out how much hydroxide was added, and there's enough data there, 0.02478 liters times 0.150 moles per liter will tell us how many moles of sodium hydroxide reacted. That's the same as the number of moles of benzoic acid that are present. Convert that into grams. I believe the molecular weight of benzoic acid is 122 grams per mole. And you should get a number that's less than 0.7529 grams. Let's see. The mass in grams. Oh, so yeah, and so you get it, and that's it. You write it down. And there it is. So let's see if we did it the same way. 0.02478 liters times 0.150 moles per liter, and that is the same as the moles of benzoic acid. So that's the moles, 122 grams per mole. We use 0.453 grams of benzoic acid. They must have asked what is the percent benzoic acid in the sample, and that if they did, and I can't believe they didn't, it would be 0.453 divided by the 0.7529 times 100, which I believe I remember answering this before. It's 60.2%. Here it is. 60.2%, and that is the last part, and I have lost track of what that 2 means. It's like question number 1, part 5, letter something, number something, letter something. So you just write the last part, the little 2, and that is the percentage of benzoic acid in the sample to 3 significant figures.